Hello everybody, this is a supplementary video on Newton's laws, force interactions, and their applications. The reason we need to understand forces, how to draw free body diagrams, and how to do a summation of force is due to Newton's laws of motion. Newton's laws of motion are the foundations of classical physics as they describe how objects and their surroundings have forces on one another. Newton's first law of motion is that an object is at equilibrium when the object is either at rest or moving with a constant velocity. This means that when we sum all of the forces in the system, they will be equal to zero. This is called the law of inertia. Most commonly, we hear it as an object in motion stays in motion, an object at rest stays at rest unless acted upon by an unbalanced net force. Newton's second law states that the acceleration of an object is directly proportional to the net forces acting on the object and inversely proportional to the mass of the object. This means that as we sum all the forces in the system, they will be equal to the mass times the acceleration of the object. Newton's third law of motion is that if object A exerts a force on object B will exert an equal magnitude but opposite direction force back onto A. If this equal and opposite force is normally denoted as the normal force. For instance, if we have a person push against the wall will not fall down. Instead, the wall will push back on the person with the same force to ensure that it can stay standing. In order to better understand Newton's laws, we first need to understand what a force is. A force can either be denoted as a push or a pull. It is an interaction between two objects. A force is always denoted with a vector quantity. Therefore, we put an arrow above it. The first force we are going to discuss is gravitational force. This can also be called the weight of an object, and this is the force of the pull of gravity on an object. Therefore, it can be found by multiplying the mass of the object times the gravitational acceleration on the object. Most commonly, we are solving for gravitational force on Earth. Therefore, our acceleration is going to be 9.1 meters squared per second or 32 feet per second squared. When we are drawing gravitational force, we always draw them straight down to Earth or the planet that they are taking into account on. The next force we're going to discuss is the normal force. This is the force that happens when an object is on a surface. Because the object exerts a force onto the surface exerts an equal but opposite force back onto the object. When drawing the normal force, we always draw it perpendicular to the surface that the object is touching. Think about when a person is standing on a scale. The weight that is shown on the scale is the normal force. Yet, if someone were to push down on the person, the force coming off the scale is going to be higher. This doesn't mean that the person weighs more, it just means that there's more force pushing down, which the scale will notice. The next important force that we're going to discuss is the friction force. In addition to normal force, friction force is also an exerted force, and it is a contact force. Friction force is solved as the coefficient of friction, denoted as mu, times the normal force. In most cases, we draw this force is drawn down parallel to the surface and in the opposite direction in which the object is moving. If the object is moving to the right, this will be the friction force. If the object is moving to the left, the friction force would be opposite. And there are many other forces besides this, such as tension, spring, and contact forces, but now we're going to move on to force decomposition, which is a very common problem in physics as it's where we draw our forces. In this figure, we have a box that's being pulled by a rope at an angle of theta. When drawing this force, we denote it with the vector symbol, so an arrow over it. Since our force is not parallel or perpendicular to the object, we need to decompose this into x and y vectors in order to solve our problem. Our x vector is going to be over here in the x direction, and our y vector is going to be pointed up. We need to use trigonometry in order to solve for what these are going to be. Looking at our force right now, our f of x is going to be f times the cosine of theta, and our y direction is going to be f times sine of theta. One of the reasons that we decompose our forces is so that we can work with objects on a ramp. Looking at this figure, you can see an object, and that is being pulled at an angle with their force, and it's also resting on an angle. We are going to draw our normal force, which will be perpendicular, our gravitational force, which is going to be straight down, and then our pulling force, which is at an angle. But as we can see, our pulling force is in both the x and y direction. So let's instead shift our axes so that we can be in the same x and y direction. Now we can see that we have a positive pulling force in our y direction as well as our normal force in the y direction, and we're going to have a positive direction for our pulling force in the x direction. This decomposition just helps us to be able to use our angles and trigonometry to solve everything. In order to solve problems in physics, we start by drawing free body diagrams. These diagrams, we have an object that we are focusing on, and then all the forces that are acting upon the object. Earlier we discussed how to draw forces, so let's practice this out. Say we have a force pulling on our object in these two directions. We're also going to have gravitational force coming down in these directions as we are decomposing it, so it's split in both x and y. And since this is on a ramp, we're going to have normal force. Let's pause the video and take a second to draw where we think our normal force is if the ramp is right below the box like before. Alright, our normal force is going to be pointing up in a perpendicular direction. From this diagram, we are able to see that the free body diagram is going to be all of this. Now that we have everything set, we're able to use our free body diagram to help us sum our forces. This means that the sum of all of our forces is going to be equal to 0 because our object is at 0. The full summation is going to be an addition of all of our forces, both in our x and our y direction. But we are able to decompose this because we split up our force vectors. So we're going to have a summation in the y direction, which will have all of our y components, and a summation in the x direction, which will have all of our x components. And that's going to be the end of our supplementary force video with Newton's laws. Thank you.